The Andromeda Galaxy looks like a faint blur in the night sky, but that tiny glow hides a structure so enormous that its visible disk is only the beginning. Beyond its spiral arms lies a vast halo of ancient stars, invisible gas dark matter, and smaller galaxies held within its gravity. Tonight the journey moves from Andromeda's distant outer boundary to the strange black hole at its center. If calm journeys through the universe bring the night to life, please like this video, subscribe to the channel and settle in as the true scale of Andromeda slowly unfolds. Far beyond the bright band of the Milky Way, the Andromeda Galaxy occupies a quiet place in the nearby universe. It appears from Earth as a faint, elongated glow in the northern sky, yet that small patch of light represents an enormous island of stars. The galaxy lies about 2.5 million light-years from the Milky Way. At that distance, the light now reaching Earth begins its journey long before modern humans appear. The view, therefore, shows Andromeda not as it is at the present moment, but as it exists in a remote part of the past. Andromeda belongs to the local group, a collection of galaxies held together by their shared gravity. The local group stretches across several million light-years and contains dozens of known members. Most are small dwarf galaxies, faint systems with far fewer stars than the two dominant spirals. The Milky Way and Andromeda contain most of the group's visible mass and most of its stars. A third large spiral, the Triangulum Galaxy, is smaller than both, but still much greater than the surrounding dwarfs. Together, these galaxies form a loose community rather than a dense cluster. From Earth, Andromeda lies in the direction of the constellation Andromeda, but the constellation is only a pattern created by nearby stars in the Milky Way. Those foreground stars stand vastly closer than the galaxy behind them. Through a dark sky, the galaxy can sometimes be seen without a telescope as a soft mark, slightly wider than the full moon. Only its bright central region is usually visible to the unaided eye. The full galaxy extends across a much larger area of the sky, but its outer light is too faint for ordinary vision. This contrast between apparent faintness and true size begins with distance. The galaxy is immense, yet its light spreads thinly across space before reaching Earth. Measurements of Andromeda's distance rely on several independent methods. Astronomers study stars whose true brightness can be estimated from regular patterns in their light. By comparing that known brightness with how faint the stars appear, they calculate the distance between Earth and the galaxy. Other methods examine stellar populations, exploding stars, and the structure of the galaxy itself. These approaches do not produce one perfectly fixed number because every measurement carries uncertainty. Observations constantly place Andromeda at roughly 2.5 million light-years away. Small differences among studies remain, but they do not change its position as the nearest large spiral galaxy to the Milky Way. The local group itself lies on the edge of a much larger arrangement of galaxies. Nearby groups and clusters form part of a broad cosmic pattern shaped by gravity over billions of years. Within that pattern, the local group is a modest structure. It contains no giant elliptical galaxy and no crowded central region filled with hundreds of large systems. Even so, the group is not static. Every galaxy follows a path determined by the combined pull of visible matter and dark matter. Andromeda and the Milky Way move toward each other while smaller galaxies travel on more varied orbits around them. Andromeda's motion can be measured through changes in the wavelengths of its light. The galaxy approaches the Milky Way along the line of sight, producing a shift toward shorter wavelengths. Part of this motion comes from the movement of the Sun around the Milky Way, and part reflects the true relative motion of the two galaxies. After those effects are separated, observations indicate that Andromeda continues to approach. Its sideways motion is more difficult to measure because the apparent change is extremely small. Careful studies show that the two great galaxies are gravitationally bound and are likely to interact in the distant future. Within the present local group setting, this approach is simply one part of a slow, continuing motion. The separation between Andromeda and the Milky Way is enormous by ordinary standards, yet it is not especially large compared with the size of the local group. Light needs millions of years to cross the gap. A spacecraft moving at the speed of the fastest human-made probes would require far longer than the age of recorded history to travel between them. The distance, therefore, preserves each galaxy as a separate world of stars, gas, dust, and unseen mass. Their mutual gravity acts across the gap, but no ordinary exchange occurs on human timescales. The space between them contains thin gas, isolated stars, and small galaxies, though most of the volume is nearly empty. The Triangulum Galaxy lies farther from the Milky Way than Andromeda does and may be gravitationally connected to Andromeda. Its exact past orbit remains uncertain because its motion is difficult to reconstruct across billions of years. Some observations suggest that it has interacted with Andromeda, while other studies allow a more distant history. This uncertainty reflects the challenge of reading galactic motion from a brief moment of observation. Astronomers see positions and velocities in the present, then use physical models to explore possible histories. The local group becomes a moving system whose full story is written across timescales far longer than any direct human record. Smaller galaxies also reveal the reach of the group. Some orbit the Milky Way, some orbit Andromeda, and others occupy more isolated positions. Their stars often contain ancient populations formed early in cosmic history. Their faint light makes them difficult to detect, so the known membership continues to change as surveys become more sensitive. The total number of dwarf galaxies is therefore not final. Observations indicate that many extremely dim systems may remain undiscovered. Their presence matters because they trace the distribution of mass and the long gravitational history of the group. Seen from this widest local scale, Andromeda is both distant and familiar. It is distant because millions of light years separate its stars from the solar system. It is familiar because it belongs to the same small galactic neighborhood as the Milky Way. Its light crosses the dark space between two major members of one gravitational family. The faint glow in the sky is therefore not an isolated object beyond all connection. It is a neighboring galaxy within the local group, moving slowly through the same broad field of gravity, carrying hundreds of billions of stars across the nearby universe. Andromeda's influence extends far beyond the region that shines clearly in visible light. A galaxy does not end where its last bright star can be seen. Its gravity reaches into a much larger volume, shaping the paths of stars, gas dwarf galaxies, and streams of material across immense distances. This surrounding domain is not marked by a sharp edge. Instead, the strength of Andromeda's pull gradually weakens with distance, while the influence of the Milky Way, the Triangulum Galaxy, and the wider local group becomes more important. The idea of a gravitational sphere of influence describes the broad region in which Andromeda acts as the main force guiding nearby objects. The boundary is approximate because gravity from several galaxies overlaps throughout the local group. A small galaxy near Andromeda may be bound to it, while another at a similar distance may follow a different path because of its speed and direction. Position alone does not determine membership. Motion mass and the long history of interaction all affect whether an object remains connected to Andromeda. Astronomers estimate Andromeda's total mass by studying the movement of stars, gas, and companion galaxies. Visible matter explains only part of the observed motion. Stars far from the center travel faster than they would if most of the mass were concentrated in the bright disk and bulge. This pattern indicates the presence of a much larger amount of unseen matter distributed around the galaxy. The unseen component is called dark matter, because it does not emit, absorb, or reflect light in the ordinary way. Its presence is inferred from gravity. The total mass assigned to Andromeda remains uncertain. Different methods produce values that can vary by a large amount, partly because the outer regions are difficult to observe and partly because the motions of companion galaxies depend on incomplete orbital histories. Many estimates place Andromeda's mass near 1 trillion times the mass of the Sun, though some studies suggest lower or higher values. The Milky Way may be lighter, similar in mass, or possibly heavier. Observations continue to refine the comparison, and no single measurement fully settles it. A galaxy with such mass controls a vast region. Its gravitational reach may extend several 100,000 light-years from the center, depending on how the boundary is defined. One useful boundary is the distance within which matter is likely to remain gravitationally bound to the galaxy. Another is based on the region where the average density falls to a chosen level above the background density of the universe. These definitions are practical tools rather than physical walls. Material can cross them, and the edges change slowly as the galaxy grows and interacts. Within this broad domain, small companion galaxies move along long orbits. Some travel close to Andromeda and experience strong tidal forces. Tidal force is the difference in gravitational pull across an object. The side of a dwarf galaxy nearer Andromeda feels a slightly stronger attraction than the far side. Over time, this difference can stretch the smaller system, remove stars, and alter its shape. A companion that passes repeatedly through the inner part of Andromeda's influence may lose much of its original structure. Other companions remain far away where Andromeda's pull is weaker but still important. Their orbits can last billions of years. Because only a short part of each orbit is observed, directly astronomers use present positions and velocities to model possible paths. These models depend on the estimated mass of Andromeda and on the gravitational effects of other local group members. Small changes in the starting conditions can lead to different past histories. As a result, the exact classification of some distant dwarfs remains uncertain. The space governed by Andromeda is not empty. It contains extremely thin gas-isolated stars, dark matter, and fragments left by earlier interactions. The density is far lower than in the visible disk, yet the total volume is so great that widely scattered material can still contribute significant mass. Gas in this region may move slowly toward the galaxy, remain suspended in a hot, diffuse state, or be pushed outward by energetic events. Its motion reflects a balance among gravity, pressure, heating, and past activity. The outer influence of Andromeda also meets the influence of the Milky Way. Between the two galaxies lies a region where neither system acts alone. Gravity from both major galaxies, together with the mass of the wider local group, shapes the movement of matter there. The exact location of any dividing surface changes with time because the galaxies approach each other and because their mass distributions are not simple spheres. The border is therefore better understood as a broad transition than as a fixed line. This overlapping field affects the smaller galaxies between them. Some may have changed allegiance during the history of the local group, passing from the control of one large galaxy to another. Others may follow paths around the combined mass of the entire group. Evidence for such transfers is difficult to confirm because orbital information becomes less certain farther back in time. Observations indicate that galactic environments are active and changing even when their motion appears still on human time scales. Andromeda's sphere of influence also provides a measure of its true scale. The bright disk is only the central visible portion of a much larger gravitational system. Light reveals stars and glowing gas, but gravity reveals the extended structure that contains them. A galaxy is therefore not merely a flat wheel of stars, it is a deep, three-dimensional region in which visible matter occupies a relatively small inner part, surrounded by a much broader distribution of unseen mass and sparse material. Across this region, every orbit records the pull of the whole galaxy. A dwarf companion, a detached star, or a cloud of gas responds not only to nearby matter but also to the combined mass spread across Andromeda's vast surroundings. The resulting paths are slow-curved and often complex. Together, they define a domain that reaches far into intergalactic space, establishing Andromeda as one of the two main gravitational centers of the local group, and giving the galaxy a scale far greater than its visible light alone suggests. This extended control forms the outermost measure of the galaxy expressed through motion balance and the persistence of gravity across space. The dark matter halo surrounding Andromeda forms an immense invisible structure around the galaxy. It cannot be photographed directly because dark matter does not shine, scatter light, or produce ordinary spectral lines. Its presence becomes clear through motion. Stars, gas clouds, and small galaxies travel as though far more mass exists than telescopes can see. Their speeds reveal a broad gravitational field extending well beyond the bright disk, creating a deep envelope whose size exceeds the visible galaxy many times. Near the center, stars move under the combined pull of the bulge disk, gas dust, and dark matter. Farther outward, visible matter becomes thinner, yet orbital speeds remain unexpectedly high. If only luminous material were present, stars near the edge would move more slowly because most known mass would lie behind them. Instead, their motion indicates that substantial mass continues to surround them. This pattern is called a flat rotation curve, meaning that orbital speed changes far less with distance than visible matter alone would predict. Andromeda's rotation curve has been studied through the motion of neutral hydrogen gas and other traces spread across its disk. Radio observations show that cold hydrogen can be detected far beyond regions bright in visible light. The gas shifts in wavelength according to its motion, allowing astronomers to estimate how quickly different parts of the galaxy rotate. These measurements show that gravity remains strong across distances. The unseen mass required to explain this motion is distributed through a halo rather than concentrated only in the center. The halo is usually modeled as roughly spherical, although its true shape may be flattened, stretched, or uneven. Dark matter does not settle into a thin, rotating disk. Gas loses energy through collisions and radiation, allowing it to collapse into a plane. Dark matter appears to interact mainly through gravity, so it remains spread through a broader volume. Computer simulations suggest that large halos grow through repeated mergers of smaller dark matter structures, producing forms that are not smooth or symmetrical. The density of dark matter is expected to be greatest toward the inner regions and to decline gradually with distance. Several mathematical profiles describe this decline, but observations do not select one exact form for Andromeda at every radius. The inner distribution is difficult to separate from the mass of stars and gas, while the outer distribution is difficult to measure because traces become sparse. Estimates, therefore, depend on assumptions about stellar mass, orbital patterns, and the shape of the halo. Although the halo is vast, dark matter within it is diffuse. A large amount of mass is spread across an enormous volume. Individual dark matter particles, if they are particles, pass through ordinary matter with little detectable interaction. Their nature remains unknown. Observations establish the gravitational effects of dark matter across galaxies and clusters, but they do not identify the substance responsible. Proposed explanations include undiscovered particles, while alternatives attempt to modify gravity. Current evidence broadly supports dark matter, though its microscopic identity remains uncertain. The estimated mass of Andromeda's halo depends on how far outward the measurement extends. Inner rotation provides information about the central portion, while distant stars, globular clusters, and companion galaxies probe larger radii. Each tracer follows a different path and may not move in a settled orbit. A recent encounter, tidal disturbance, or unusual trajectory can distort the estimate. Astronomers, therefore, combine many objects and compare several models rather than relying on one measurement. Globular clusters provide valuable evidence because they orbit far from the bright disk. These compact groups contain old stars bound tightly together, but each cluster moves through Andromeda's gravitational field. Their speeds and positions help trace mass where the stellar disk becomes faint. Planetary nebulae glowing shells released by aging stars also serve as motion tracers. Together with remote halo stars, they reveal that Andromeda retains substantial mass far outside its brightest regions. The outer halo may extend several 100,000 light-years from Andromeda's center. Its precise edge is not directly visible and depends on the definition used. Astronomers often choose a radius within which the average density reaches a specified multiple of the cosmic background density. This produces a useful estimate for comparing galaxies, but the dark matter distribution does not suddenly stop there. Density continues to fade outward until Andromeda's halo blends into the larger gravitational environment of the local group. Dark matter also affects the stability of the visible disk. Its broad gravitational field helps determine how stars orbit and how the disk responds to disturbances. The halo can absorb angular momentum, the measure of rotational motion during slow gravitational interactions. This exchange influences the shape and movement of large structures within the galaxy. However, the exact response depends on the halo's density, rotation, and internal structure, all of which remain partly constrained by observation. Computer models of Andromeda place its dark matter halo within the history of galaxy formation. In these models, small regions of dark matter collapse, first under gravity. They merge into larger structures, drawing ordinary gas into their gravitational wells. The gas cools and forms stars while dark matter remains extended. Over billions of years, continued mergers add mass to the halo and leave smaller concentrations within it. Some may contain dwarf galaxies, while others may remain dark because they never gather enough gas to form visible stars. These predicted smaller concentrations are called subhalos. Simulations produce many more subhalos than the number of known luminous companions. This difference may occur because most small halos cannot retain gas after the early universe is heated by radiation, or because stellar explosions remove their remaining material. Some may contain no stars. Searches for their gravitational effects continue using stellar streams, motions, and distortions in visible matter. Evidence supports a clumpy halo, but the number and masses of its unseen substructures remain uncertain. Andromeda's dark matter halo therefore defines an enormous hidden framework. It guides rotation, binds distant objects, supports the galaxy's extended gravitational reach, and preserves traces of ancient assembly. Though invisible, its influence appears in every measured orbit across the galaxy's outer volume. The bright spiral seen from Earth occupies only a small part of this structure. Around it lies a broader reservoir of unseen mass, quiet, in appearance dominant in gravity and essential to the true scale of Andromeda. Around Andromeda, a population of smaller galaxies moves through the gravitational field of the larger system. These companions are known as satellite galaxies because their paths are shaped by Andromeda's mass. Most are dwarf galaxies containing far fewer stars than a spiral. Some appear as faint rounded clouds of old stars, while others have irregular forms shaped by internal activity and repeated gravitational disturbance. Together, they reveal that Andromeda is not a single isolated galaxy, but the central member of a family spread across a region of space. The two brightest companions are called Messier 32 and Messier 110. Messier 32 is a compact elliptical galaxy projected close to Andromeda's central area. It contains a dense concentration of stars and lacks the spiral structure seen in its larger neighbor. Its compact form may reflect a history of interaction, though the exact sequence remains uncertain. Messier 110 is more extended and diffuse. It appears elongated, contains older stars, and shows signs that its structure has been altered by Andromeda's gravity. Many other satellites are fainter. They are usually identified by surveys that search for concentrations of stars against the foreground of the Milky Way. Because these systems have low surface brightness, their light is spread thinly across the sky. A dwarf galaxy may contain thousands or millions of stars and still remain difficult to detect. Digital cameras, telescopes, and methods allow astronomers to recognize patterns that earlier observations could not separate from the surrounding star field. The known satellites receive names based on their positions, survey designations, or order of discovery. Several are called Andromeda, followed by a number. Their properties vary widely. Some are dwarf spheroidal galaxies, systems dominated by old stars with little remaining gas and almost no present star formation. Others are dwarf irregular galaxies with less ordered shapes and, in some cases, small amounts of gas. A few objects remain difficult to classify because their structures have been stretched or partly dissolved. Satellite galaxies occupy a large three-dimensional volume around Andromeda. Their apparent positions on the sky provide only two coordinates, while distance measurements reveal how far they lie in front of or behind the main galaxy. These distances are not precise for every system. Astronomers often use the brightness of particular stars, especially stars at known stages of evolution, to estimate the separation. Small uncertainties can change the reconstructed arrangement, so the spatial pattern remains open to refinement. One striking feature is that many satellites appear to lie near a broad, thin plane. Some also seem to move in a shared direction. This arrangement has attracted attention because standard models of galaxy formation usually produce satellite systems with a range of orbital orientations. Observations indicate that the planar structure is real, but its long-term stability and origin remain uncertain. It may reflect a temporary alignment, a shared history of infall, an ancient interaction, or a combination of effects not yet fully understood. The motions of these satellites provide information about Andromeda's mass. A companion moving rapidly at a great distance requires a strong gravitational field to remain bound. By comparing positions and velocities, astronomers estimate the amount of matter enclosed within the satellite's orbits. The method is difficult because only a small portion of each orbit is observed. Sideways motion is especially challenging to measure at Andromeda's distance. Models therefore include broad uncertainties and must account for companions that may be entering the system for the first time. Each satellite also contains its own internal gravity. The motions of stars inside dwarf spheroidal galaxies often indicate that dark matter dominates their mass. Their visible stars may be sparse, yet those stars move too quickly to be held together by luminous matter alone. These small systems therefore act as laboratories for studying dark matter on scales far below that of Andromeda itself. Their simplicity is useful, although tidal disturbance can complicate measurements by changing stellar motions. As satellites orbit Andromeda's tidal forces gradually reshape them. Stars near the outer edge of a dwarf galaxy are only weakly bound. During a close passage, some can be pulled away and placed into long streams. Gas may also be removed by gravity or by pressure from the thin material surrounding Andromeda. Repeated passages can reduce a once larger companion to a faint remnant. The surviving core may continue orbiting while its lost stars spread across the halo. Not every satellite follows the same history. Some may have formed near Andromeda, while others may have entered as members of smaller groups. A dwarf can arrive with its own companions, creating related paths among several systems. Interactions between satellites are also possible, especially before they become deeply bound to Andromeda. The present arrangement therefore records many overlapping events rather than one simple pattern. Chemical compositions, stellar ages, and orbital directions help separate these histories. The Triangulum Galaxy occupies a special position in this wider family. It is much larger than the ordinary dwarf satellites and is the third major spiral in the local group. Some models place it on a long orbit around Andromeda, while others allow a path influenced by the combined gravity of the local group. Measurements of its motion continue to improve, but its exact relationship to Andromeda remains uncertain. It may have approached closely in the past, though evidence for such an encounter is still debated. The satellite system also reveals how incomplete the observed census remains. Surveys find new ultra-faint galaxies as instruments become more sensitive. Some predicted companions may contain so few stars that they are nearly invisible. Others may lie behind dense foreground regions where Milky Way stars and dust make detection difficult. The number of known satellites is therefore a lower limit rather than a final total. Their distribution will become clearer as wider and deeper observations cover more of the surrounding sky. Across Andromeda's outer domain, these small galaxies move slowly through darkness, each carrying a separate record of star formation, gas loss, and gravitational change. Some remain intact, some are distorted, and some approach dissolution. Their paths trace the mass of the larger galaxy, while their stars preserve fragments of the local group's long cosmic history. Seen together, they enlarge the meaning of Andromeda from one luminous spiral into a broad system of companions bound within its gravity. Beyond Andromeda's bright disk, a vast and faint population of stars forms the stellar halo. This halo is not a smooth shell with a clear surface. It is a loose, extended region where stars are scattered across enormous distances, separated by wide stretches of darkness. Most of these stars are too dim to be seen without powerful telescopes. Together they reveal that the visible spiral is surrounded by a larger structure made from some of the galaxy's oldest stellar populations. The stellar halo differs strongly from the bright disk. In the disk, stars follow ordered paths around the center and are concentrated near a flattened plane. In the halo, their motions are more varied. Some travel on steeply tilted orbits, some move far above and below the disk, and others follow elongated paths that carry them through a large volume. This mixture creates a roughly rounded distribution rather than a thin, rotating layer. The halo therefore extends in every direction even though its light remains weak. Astronomers study these stars by resolving them one by one. Andromeda is distant, but its brightest individual stars can still be detected with large telescopes. Surveys measure their colors and apparent brightness. These properties reveal temperature, age, and stage of stellar evolution. Red giant stars are useful because they are luminous and common among old populations. By counting them across different regions, astronomers map the density of the halo and estimate how far it extends. The density decreases gradually with distance from Andromeda's center. Near the disk halo, stars are easier to find because they are more numerous. Farther outward, the population becomes sparse, and only deep observations can separate its members from foreground stars in the Milky Way and from distant background galaxies. Statistical methods identify which points of light probably belong to Andromeda. Measurements of motion and chemical composition provide further confirmation, though these observations become increasingly difficult for faint stars. The halo reaches across several 100,000 light-years, although its exact boundary remains uncertain. There is no single radius where the stellar population ends. Instead, the number of stars declines until they become difficult to distinguish from other objects in the surrounding sky. Some studies detect stars at distances comparable to the outer range of Andromeda's satellite system. These stars remain gravitationally connected to the galaxy, but their distribution is thin and uneven. Most halo stars are old. Many formed billions of years ago when the universe was much younger and heavy elements were less abundant. Astronomers describe a star's abundance of elements heavier than helium as its metallicity. The term does not mean the star is made mainly of metals. Hydrogen and helium still dominate. A low metallicity indicates that the material from which the star formed had experienced fewer generations of stellar enrichment. Andromeda's halo contains many low metallicity stars, but it is not chemically uniform. Some regions contain stars richer in heavy elements than others. This variation indicates that the halo does not arise from a single event. Different stellar populations form in separate environments and later become part of the same extended structure. Their chemistry preserves information about the gas available when they formed and about the sizes of the systems that produced them. Stars born in small dwarf galaxies often show different chemical patterns from stars formed in larger systems. A small galaxy forms stars slowly and may lose gas easily, limiting the buildup of heavy elements. A larger galaxy can retain enriched gas and continue forming new generations. When stars with different chemical histories appear in the same halo, their composition helps astronomers trace their origins. This evidence shows that Andromeda's outer stellar population contains several distinct components. The ages of halo stars are estimated from their brightness and color, especially when observations reach faint stages of stellar evolution. The most precise age measurements require detecting stars near the point where they leave the long period of hydrogen burning in their cores. At Andromeda's distance, this demands long observations with sensitive instruments. Results indicate that many halo populations are ancient, while some contain stars formed later. The age range again suggests a complex history. Globular clusters also inhabit the stellar halo. Each cluster is a dense, nearly spherical collection of stars held together by its own gravity. Many contain old, low metallicity stars and orbit far from the disk. Andromeda possesses a population of these clusters, including examples at great distances from the center. Their positions and motions define the structure of the halo. Their chemical properties provide another record of early star formation and the environments in which they developed. The stellar halo contributes only a small fraction of Andromeda's total visible light. Its importance comes from its scale and history rather than brightness. The disk contains far more stars packed into a smaller volume, while the halo spreads fewer stars across a much larger region. Seen from a great distance, most of this outer light disappears into the background. Detailed observations reveal that the galaxy's luminous matter extends beyond the familiar oval shape. The halo is also uneven. Star counts vary from one field to another, and some regions appear denser or more metal-rich than nearby areas. This irregularity shows that the outer galaxy is not fully mixed. The orbital periods of distant stars can last billions of years, so differences in their distribution may survive for a long time. Gravity slowly redistributes them, but the process remains incomplete across the enormous volume. At these distances, the distinction between halo stars and free stars in the local group can become unclear. A star may be only weakly bound to Andromeda, especially after strong gravitational disturbance. Determining its status requires knowledge of its position and full motion, which is rarely available. Astronomers, therefore, describe the halo through probabilities and density patterns rather than assigning every distant star with certainty. The faint stellar halo gives Andromeda a broad, luminous presence beyond its bright, spiral form. Ancient stars move through this outer region on slow and varied paths carrying chemical records from early periods of galaxy formation. Their weak light maps a structure that is rounded, extended, and complex. Though sparse, they remain part of Andromeda's visible body, enlarging the galaxy far beyond the portion easily seen and preserving a quiet archive of its earliest stellar generations. Around Andromeda's stellar halo, structures of stars reveal places where smaller galaxies have been stretched apart. These structures are called stellar streams. They appear as narrow arcs, broad clouds, shells, or irregular concentrations against the smoother background of the halo. Each stream contains stars that once belonged to another system or to a compact part of Andromeda. Gravity removes them gradually, leaving patterns that can survive for billions of years. A stellar stream forms when a smaller galaxy or star cluster passes through Andromeda's gravitational field. The pull is stronger on the side nearest Andromeda and weaker on the far side. This difference creates tidal forces that draw stars away from the smaller system. Some stars move ahead along the orbit while others fall behind. Over time, they form tails that trace the path of the disrupted object. The original system may remain as a weakened core or dissolve completely. The most prominent structure is the giant stellar stream, a vast concentration of stars extending away from Andromeda's inner regions. It is visible through counts of red giant stars rather than ordinary photographs. Its stars share patterns in position, motion, age, and chemical composition. These similarities show that they belong to a common event. The stream covers many tens of thousands of light years and contains enough stars to indicate that its original galaxy was not extremely small. Astronomers examine the stream by measuring how its stars move toward or away from Earth. These line-of-sight velocities change along its length, producing a pattern expected for debris moving through Andromeda's gravity. Distance measurements show that parts of the stream lie behind the main disk from Earth's viewpoint. By combining distance and velocity, researchers construct possible orbits for the lost companion. The results indicate a close passage near Andromeda's center where strong tidal forces remove much of its material. The identity of the object that creates the giant stellar stream remains uncertain. Some models connect it with one of Andromeda's surviving compact companions, while others propose that the parent system is almost completely destroyed. The remaining core may be hidden near the bright central regions or dispersed among other debris. Different simulations reproduce parts of the observed structure with different starting conditions. Observations establish the merger, but they do not yet provide one complete history. The stars within the giant stellar stream are not all extremely metal-poor. Many contain a moderate abundance of elements heavier than helium, suggesting formation in a galaxy more massive than the faintest dwarf companions. A larger system can retain enriched gas and produce several generations of stars before disruption. The stream also contains a range of stellar ages. This mixture supports a complex parent galaxy with an extended period of star formation rather than a single ancient population. Beyond the giant stellar stream, Andromeda's halo contains additional features. Broad stellar clouds appear on different sides of the galaxy. Thin streams connect some remote globular clusters, while curved shelves of stars form sharp changes in density. These shelves can develop when tidal debris reaches the farthest point of an elongated orbit and slows before falling inward. Stars gather near these turning regions, producing edges and arcs that remain visible against the surrounding halo. Several structures may arise from the same merger. A disrupted companion does not release all of its stars at once. Material removed during separate passages follows related but distinct paths. One group may form a long stream while another spreads into a shell or cloud. Computer simulations follow particles through a model of Andromeda's gravitational field to test whether one encounter can produce the observed arrangement. Successful models connect distant features into a shared orbital history. Other streams have separate origins. Small dwarf galaxies and globular clusters continue to lose stars as they move through the halo. Their debris is thinner and fainter than the giant stellar stream. Some features contain only a small number of detectable stars, making their boundaries uncertain. Foreground stars from the Milky Way and distant background galaxies add confusion. Wide surveys are required to map large areas and distinguish real structures from statistical variation. Stellar streams act as sensitive tracers of Andromeda's gravitational field. Their paths depend on the distribution of mass through which they move. A smooth, spherical halo produces one kind of orbit, while a flattened or uneven halo alters the stream's direction and width. Smaller dark matter concentrations may disturb a narrow stream, creating gaps or density changes. These effects can reveal invisible structure, though uncertain initial conditions and overlapping debris make interpretation difficult. The width of a stream provides clues about its source. A compact globular cluster releases stars with similar speeds, producing a narrow feature. A dwarf galaxy has a broader internal range of motions and creates a wider stream. Chemical composition strengthens this distinction. Stars from one globular cluster usually share a close chemical pattern, while a dwarf galaxy often contains several populations. Measurements, therefore, combine shape, motion, age, and chemistry to identify disrupted systems. These remnants show that galaxy growth continues through accumulation. Andromeda gathers smaller systems whose stars become part of its halo. The process is called hierarchical assembly, meaning that large structures develop through combinations of smaller ones. The phrase describes a broad pattern rather than a perfectly ordered sequence. Some mergers occur early, others later, and each contributes material in a different form. Andromeda's outer regions preserve this process clearly because stars there mix slowly. Streams gradually lose their sharp form. Stars with slightly different orbital periods spread along their paths, while repeated passages through changing gravitational fields increase their separation. After enough time, the debris blends into the general halo, and its common origin becomes difficult to recognize. A visible stream, therefore, represents an event that is relatively recent or not yet fully mixed. Older mergers may survive only as unusual chemical groups or subtle patterns in stellar motion. Across these structures, stars follow paths established by encounters long past. They no longer form one compact galaxy, yet they retain enough shared motion and composition to reveal their connection. Their shapes show how Andromeda's gravity works across great distances, drawing smaller systems apart and spreading their contents through the halo. The streams and debris make the outer galaxy an archive of assembly, written in faint bands of old starlight. Andromeda is surrounded by a vast atmosphere of extremely thin gas that extends far beyond its bright stars. This material is called the circumgalactic medium, meaning the gas around a galaxy. It occupies the space between the visible disk and the more distant intergalactic environment. Although it is difficult to see directly, it contains a large amount of ordinary matter spread through an enormous volume. The circumgalactic medium is not a uniform shell. Its density, temperature, and composition change from place to place. Some regions contain hot ionized gas, in which atoms have lost one or more electrons. Other regions hold cooler clouds that remain partly neutral. These phases overlap and move through one another under the influence of gravity, pressure radiation, and past galactic activity. Their combined structure is irregular and constantly changing. Most of this gas is too faint to detect through its own light. Astronomers often study it indirectly by observing distant background objects. When light from a remote quasar passes through Andromeda's surroundings, atoms in the gas absorb specific wavelengths. These absorption patterns reveal which elements are present, how quickly the gas is moving, and whether it is approaching or receding. By comparing many sight lines, researchers estimate the size and distribution of the surrounding medium. Observations indicate that Andromeda's circumgalactic gas reaches hundreds of thousands of light-years from the galaxy. In some directions, its outer regions may extend far enough to overlap with the corresponding gas around the Milky Way. The exact boundary remains uncertain because the density decreases gradually rather than ending at a sharp surface. At great distances, Andromeda's gas blends into the thin material of the local group. The total mass of this medium is significant. Galaxies contain less visible ordinary matter than expected from measurements of the early universe. Some of the missing material appears to reside in extended gaseous halos. Around Andromeda, the circumgalactic medium may contain a mass comparable to a substantial fraction of the stars in the galaxy. Estimates vary because the gas is diffuse, uneven, and present across several temperatures that are not equally easy to observe. Hydrogen remains the dominant element as it does throughout most of the universe. Helium is also abundant, while heavier elements occur in smaller amounts. These heavier elements are important because they show that some gas has passed through stars. Stellar interiors create elements such as carbon, oxygen, silicon, and iron, and later return them to space through winds and explosions. Their presence in the outer halo indicates that material has moved outward from Andromeda's star-forming regions. Gas can leave the galaxy through several processes. Massive stars release powerful winds, and supernova explosions heat nearby material to very high temperatures. Groups of such events can drive large outflows away from the disk. Active periods near the central black hole may also push gas outward, although the history and strength of such activity in Andromeda remain uncertain. Once expelled, some material travels into the circumgalactic medium rather than escaping the galaxy completely. This outward movement does not always end in permanent loss. Gravity can slow the gas, causing part of it to cool and fall back toward the galaxy. This cycle is sometimes called a galactic fountain. Material rises from the disk, mixes with surrounding gas, loses energy, and later returns. The process redistributes heavy elements and helps connect star formation in the disk with the broader environment around the galaxy. Other gas may enter Andromeda from outside. Thin streams and clouds can fall inward from the local group, carrying material that has not previously formed stars. Gas may also arrive with dwarf galaxies. As a companion moves through Andromeda's surroundings, pressure from the circumgalactic medium can strip gas from it. Tidal forces may remove additional material. The lost gas then becomes part of Andromeda's extended reservoir, mixing gradually with matter already present. Temperature strongly affects how the medium behaves. Hot gas can remain suspended across large distances because its internal pressure resists gravity. Cooler clouds are denser and may sink inward more easily. Heat flows between phases while radiation removes energy from the gas. Magnetic fields, turbulence and interactions between particles also influence the rate of cooling. These processes occur across very different scales and are difficult to reproduce fully in computer models. The motion of circumgalactic gas is therefore complex. Some clouds move inward, some travel outward, and others orbit or drift through the halo. Absorption lines show a range of velocities, but converting those measurements into three-dimensional paths is difficult. Only movement along the line of sight is measured directly. The full direction remains partly unknown, so astronomers compare observations with simulations to identify likely patterns. Andromeda's movement through the local group may also shape its outer gas. The galaxy does not sit in complete isolation. Its halo interacts with material associated with nearby companions, the Milky Way, and the wider group. These interactions can compress gas on one side, stretch it into extended features, or disturb its temperature. The resulting structure may be asymmetric, though current observations do not map every region with equal detail. The circumgalactic medium plays an important role in the long life of the galaxy. Star formation consumes cold gas, but a galaxy cannot continue forming stars indefinitely without replenishment. The extended halo acts as a reservoir from which some material may eventually return to the disk. At the same time, it receives gas expelled by stellar activity. It therefore records both the loss and recovery of matter across billions of years. Different ions trace different temperatures within this environment. Cool hydrogen leaves one pattern, while highly ionized oxygen and other elements reveal warmer or hotter regions. No single observation captures every phase. A complete estimate requires ultraviolet measurements, radio data, X-ray observations, and physical models. Each method samples only part of the gas, so the overall picture remains reconstructed rather than directly photographed. Seen as part of Andromeda's true scale, this gaseous environment is enormous yet almost invisible. It surrounds the brighter galaxy with a diffuse mixture of hydrogen, helium, and heavier elements. Its clouds carry evidence of stellar explosions, incoming material stripped satellites, and slow cooling. Though the gas is thin, its great volume gives it importance. It forms a broad active boundary through which matter enters, leaves, and circulates around Andromeda. Inside the diffuse gas surrounding Andromeda, the outer stellar disk begins as a broad faint region, where stars become more numerous and their motions become more ordered. This part of the galaxy is still far from the bright, central areas. Its light is weak, its surface brightness is low, and its structure is difficult to separate from the surrounding halo. Yet the outer disk marks the place where Andromeda's flattened form becomes clear, extending across a distance much greater than the portion visible to the unaided eye. A stellar disk is a rotating layer in which most stars move around the galactic center in the same general direction. The outer disk is thinner in density than the inner regions, but it still preserves this organized motion. Stars travel along broad paths that lie close to a common plane. Their orbits are not perfect circles, and many rise above or below the average level, but their movement differs from the more random paths of halo stars. This shared rotation helps astronomers distinguish the disk from the surrounding stellar halo. Andromeda's visible disk stretches across roughly 200,000 light-years when its faint outer regions are included. Estimates vary because there is no sharp boundary. The number of stars declines gradually with distance, and the final detectable populations depend on the sensitivity of the survey and the method used to identify disk membership. Older photographs reveal mainly the bright inner oval, while deeper observations uncover a much broader spread of stars. The galaxy therefore appears larger as instruments collect weaker light. The outer disk contains fewer stars per unit area than the inner disk. Large spaces separate the brighter concentrations, and the combined glow becomes difficult to detect against the night sky. Astronomers often count individual red giant stars rather than measuring smooth light. These stars are luminous enough to be observed at Andromeda's distance. Their positions create maps of the disk even where the total surface brightness falls below the level that ordinary imaging can show clearly. Star counts reveal that the disk does not end evenly in every direction. Some regions extend farther than others, and the outline is disturbed by past gravitational interactions. The outer edge contains clumps, arcs, and variations in density. Part of this unevenness may come from stars pulled into altered paths by satellite galaxies. Part may result from earlier mergers whose debris has settled into rotating structures. The distinction between a disturbed outer disk and nearby stellar debris can therefore be difficult to define. The ages of outer disk stars cover a wide range. Many are old, showing that the disk has existed for billions of years. Other populations are younger and may have formed from gas compressed in remote regions. The rate of star formation is much lower than in denser parts of the galaxy because cold gas is limited and spread thinly. Even so, local pockets can provide enough material for new stars. These pockets remain small compared with the full scale of the disk. Chemical composition changes across the disk. Stars near the outer regions often contain fewer heavy elements than stars formed closer to the center. This pattern is called a metallicity gradient, meaning that the abundance of elements heavier than helium changes with distance. The trend develops because inner regions usually experience more generations of star formation. Each generation returns enriched material to the surrounding gas, allowing later stars to form with a greater supply of heavy elements. The gradient is not perfectly smooth. Some outer stars are richer in heavy elements than expected, while some inner populations are poorer. Stellar orbits can shift over time through gravitational interactions, moving stars away from the places where they formed. Mergers can also add stars with different chemical histories. As a result, present location does not always identify birthplace. The outer disk contains a mixture of stars formed locally and stars carried outward or deposited by past events. The disk's rotation provides another way to estimate Andromeda's mass. Measurements of stellar velocities and neutral hydrogen show that orbital speed remains high across the outer regions. The visible matter becomes sparse, but the stars continue to move under a strong gravitational field. This behavior supports the presence of the dark matter halo surrounding the galaxy. The outer disk, therefore, acts as a luminous tracer embedded within a much larger invisible mass distribution. The outer disk is also thicker than a perfectly flat sheet. Stars occupy a vertical range above and below the main plane. Older populations usually have more varied motions and can form a thicker component, while younger stars remain closer to the gas layer from which they formed. Gravitational disturbances can increase this thickness by lifting stars into tilted orbits. The result is a broad layered structure rather than a single narrow surface. Andromeda's orientation affects how this structure appears from Earth. The disk is tilted steeply to the line of sight, so it is seen as an elongated ellipse rather than a circular face. One side lies closer to Earth, while the opposite side lies farther away. Dust and projection make some regions appear denser or darker than they truly are. Astronomers correct for this geometry when estimating the disk's size, brightness, and distribution of stars. At the faintest levels, separating disk stars from halo stars requires several kinds of evidence. Rotation is important because disk stars tend to share a common direction and speed. Chemical composition and age provide further clues. Position alone is not enough, especially where the outer disk becomes disturbed and diffuse. Researchers compare observations with computer models to assign stars to likely populations while accepting that some classifications remain uncertain. The outer stellar disk gives Andromeda much of its true visible diameter. It reaches far beyond the bright region, familiar in small telescopes, spreading old and young stars across a vast rotating plane. Its weak light records slow star formation, chemical change, orbital mixing, and gravitational disturbance. Though faint, it remains part of the organized body of the galaxy. Its distant stars still follow the galaxy's shared rotation, preserving the broad outline of the disk across immense and quiet distances. Across this broad edge, Andromeda changes from a sparse outer environment into a coherent stellar system, its rotating form becoming increasingly distinct within the surrounding darkness. Andromeda's outer disk does not remain in one perfectly flat plane. Far from the center, The layer of stars and gas bends upward on one side and downward on the other. This distortion is called a galactic warp. It changes the orientation of the disk across enormous distances, giving the outer galaxy a twisted form instead of a rigid sheet. The warp is clear in observations of neutral hydrogen gas. Radio telescopes trace this gas beyond the bright stellar regions where its motion reveals the changing angle of the disk. Different rings of gas orbit the center in slightly different planes. When their positions and velocities are combined, the outer disk appears tilted and curved. The distortion is not a sharp fold. It develops slowly across the galaxy, becoming more noticeable with increasing distance from the center. Stars also participate in the warped structure, although their distribution is harder to map than the gas. Outer stars occupy regions that rise above and below the inner plane. Their motions show that the warp is not a feature projected against the sky. It is a three-dimensional change in the orientation of the disk. Because Andromeda is viewed at a steep angle from Earth, modeling is required to separate the true bend from the effects of perspective. A galactic disk can warp when forces act unevenly across its outer regions. The inner disk is dense and bound, while the outer disk is thinner and easily disturbed. A passing satellite galaxy can pull more strongly on one side, changing the paths of stars and gas. The surrounding dark matter halo may influence the shape if its mass is tilted or unevenly distributed. Gas entering from outside can add material with a different direction of motion, creating a source of torque. Torque is a force that changes rotational orientation. In a warped galaxy, torque causes outer rings to tilt while they continue orbiting the center. The effect resembles a set of bands whose angles vary with distance. Each ring responds to gravity from the disk bulge halo and companions. Because these forces do not remain perfectly balanced, the orientation can change over time. The resulting warp may persist for billions of years if the disturbance continues or if the disk responds slowly. Andromeda's companion galaxies provide several sources of disturbance: Messier 32 and Messier. Messier 110 move close enough to affect the disk, while the Triangulum galaxy exerts a weaker pull across a greater distance. Smaller satellites contribute repeated uneven forces. No single companion has been proven to create the entire warp. Models can reproduce portions of the distortion with different orbital histories, so its origin may involve several interactions rather than one event. Past mergers can leave a disk misaligned with the surrounding halo. If a smaller galaxy arrives from an inclined direction, its stars and gas carry angular momentum that differs from Andromeda's rotation. As the material settles, it can pull the outer disk away from the inner plane. The inner regions resist because their gravity is stronger and their orbital periods are shorter. The outer regions respond more freely, producing a bend that records the direction of earlier accretion. The warp is not fixed in space. Different parts of the disk can precess, meaning that their tilted or orbital planes rotate slowly around the galactic center. If every ring precesses at a different rate, the structure may wind up and fade. The continued visibility of warps in many spiral galaxies suggests that they are either long-lived under certain conditions or repeatedly renewed by fresh disturbances. For Andromeda, observations show the present shape, but do not determine how quickly it changes. Gas reacts differently from stars because gas clouds collide, compress, cool, and lose energy. When tilted gas rings intersect or approach one another, pressure and shocks can alter their motion. Stars pass through the same region with far fewer collisions. This difference allows the gaseous warp to appear sharper or more extended than the stellar warp. It also means that gas can gradually settle toward a new plane, while stars preserve older orbital patterns for longer periods. The warped disk affects estimates of Andromeda's rotation. A simple model assumes that all material moves in one flat plane. If the angle changes with radius, the observed line of sight, velocity changes even when the true orbital speed remains constant. Astronomers therefore model the disk as a series of tilted rings. Each ring has its own orientation, rotation, speed, and distribution of gas. This method produces a more accurate map of the galaxy's outer motion and mass. The distortion also changes the apparent outline of Andromeda. One side of the outer disk may seem extended or displaced, while the opposite side appears compressed by perspective. Dust lanes and gas concentrations can look uneven because the line of sight passes through different thicknesses of material. Some apparent asymmetries therefore come from geometry, while others represent genuine variations in density. Detailed velocity measurements help separate these effects. Warped disks are common among spiral galaxies, showing that the phenomenon is not unique to Andromeda. Their frequency suggests that large disks remain responsive to their surroundings. A galaxy continues to receive gas, interact with companions, and move within a dark matter halo long after its main structure forms. The outer disk, being weakly bound, records these influences most clearly. Its shape behaves like a slow, gravitational response to conditions across the wider galactic environment. Within Andromeda, the warp extends across tens of thousands of light years. Stars and gas continue to orbit normally on local scales, but their shared plane changes from one region to another. There is no single moment when the flat disk suddenly becomes bent. The transition is broad and the curvature develops across many orbital paths. Seen in 3 dimensions, the galaxy resembles a vast rotating surface whose outer edges rise and fall around a more stable inner body. This bent structure adds another measure to Andromeda's scale. The galaxy is not only wide but also vertically complex, with its outer material distributed across changing planes. The warp preserves the influence of gravity accretion and long interaction without producing a rigid or permanent shape. Across this region, Andromeda remains a moving disk, twisted by forces acting over immense distances and over time scales measured in billions of years. Inside the warped outer regions, Andromeda's disk becomes denser, brighter, and more clearly organized. Stars, gas, and dust follow a broad spiral pattern around the center, although the design is not as easy to see as in a face-on galaxy. Andromeda is viewed from Earth at a steep angle, so its circular disk appears as a long oval. Dust obscures parts of the structure, and overlapping layers of stars make the spiral pattern seem less distinct. Careful observations at several wavelengths reveal that the disk contains curved arms, arm fragments, and broad concentrations arranged around the rotating galaxy. Spiral arms are not fixed bands made from the same stars forever. They are regions where matter becomes temporarily more concentrated as the disk rotates. Stars pass into and out of these regions, while gas clouds can be compressed within them. The arms remain visible because they contain a greater density of bright stars, dust, and gas than the areas between them. Their exact origin is complex. Gravitational patterns within the disk, interactions with companion galaxies, and the response of gas to the galaxy's motion may all contribute. One common explanation describes spiral arms as density waves. A density wave is a slowly moving pattern of increased concentration passing through the rotating disk. Individual stars orbit the center at their own speeds and do not remain permanently inside one arm. As they enter a denser region, their motion changes slightly, and they gather for a time before continuing onward. Gas responds more strongly because clouds can collide and lose energy. This response helps make the spiral pattern more visible than the underlying distribution of older stars. Andromeda's spiral form is not perfectly symmetrical. Some arm segments are stronger, wider, or more continuous than others. The pattern appears disturbed with sections that bend, branch, or fade. This irregularity reflects the long history of gravitational interaction. Small companion galaxies can pull on the disk and create waves that travel through it. Earlier mergers may also leave lasting changes in stellar motion. The present structure, therefore, combines internal rotation with disturbances from outside the disk. The disk contains several stellar populations. Young bright stars tend to gather where gas has recently become dense enough to form them. Older stars are spread more smoothly because they have completed many orbits and have had time to drift away from their birthplaces. This difference changes how Andromeda appears at different wavelengths. Ultraviolet light emphasizes hot, young stars. Infrared light reveals cooler stars, and dust and radio observations trace cold gas. Each view shows a different part of the same spiral organization. Dust creates dark lanes along portions of the arms. These lanes contain small solid grains mixed with gas. They absorb visible light from stars behind them and re-radiate part of the energy at longer wavelengths. Because Andromeda is tilted dust on the nearer side of the disk blocks more of the central light and appears especially prominent. The far side is less strongly outlined in darkness because much of its dust lies behind the bright stellar body from Earth's viewpoint. Gas follows the spiral structure but does not form a smooth layer. It gathers into clouds, filaments, and broad complexes. Neutral hydrogen spreads across much of the disk, while molecular gas becomes more concentrated in denser regions. Molecular gas consists mainly of hydrogen molecules and provides the cold material from which stars form. Its distribution helps outline parts of the arms, though the amount of molecular gas in Andromeda is lower than in some actively forming spiral galaxies. The motion of the disk can be measured through shifts in the light and radio emission from its material. One side of Andromeda rotates toward Earth, while the opposite side rotates away. These motions produce a broad velocity pattern across the galaxy. The speed does not rise and fall according to visible matter alone. It remains high across much of the disk, showing again that the stars and gas move within the gravitational field of the extended dark matter halo. Within the disk, rotation is not completely uniform. Material nearer the center completes an orbit in less time than material further out. This difference is called differential rotation. If spiral arms were made from fixed groups of stars, differential rotation would stretch and wind them tightly over time. Their continued broad appearance shows that the pattern is maintained or renewed through gravitational processes rather than preserved as a permanent arrangement of the same material. Bars can also influence spiral structure in many galaxies, but Andromeda's inner form is difficult to interpret because of its inclination and bright central bulge. Some observations indicate that it may contain a bar-like stellar structure. If present, this elongated concentration can guide stellar orbits and transfer rotational motion through the disk. It may help shape some spiral features. The exact size and strength of the possible bar remain under study because projection makes a clear view difficult. The thickness of the disk changes among its populations. Younger stars and cold gas remain close to the central plane because they form from a thin layer. Older stars have more varied vertical motions and occupy a thicker region. Gravitational encounters can increase these motions, lifting stars farther above and below the plane. The disk is therefore layered with a thin component embedded inside a broader distribution of older stars. Spiral arms also influence how matter moves locally. Gas entering a denser region can slow compress and become turbulent. Clouds may merge or break apart. Newly formed stars then begin their own orbits and gradually separate from the gas. Over millions of years, the visible arrangement changes even while the larger spiral pattern continues. The arms are therefore dynamic structures maintained through movement rather than still shapes. Seen across its full width, Andromeda's disk is a rotating system of overlapping patterns. Curved arms, dust lanes, stellar layers and gas complexes share the same broad plane but respond differently to gravity. Their combined light creates the familiar elongated galaxy seen from Earth. Beneath that appearance lies a changing structure in which stars pass through spiral concentrations, gas gathers into denser regions, and gravitational disturbances slowly reshape the pattern. The spiral design is therefore not a rigid decoration, but an active expression of motion across the immense stellar disk. Within Andromeda's disk, a ring of gas dust and young stars forms a prominent galactic structure. It lies beyond the bright bulge and circles much of the disk at a distance of roughly 30,000 light-years from the nucleus. Because Andromeda is tilted from Earth, the ring appears as a series of bright arcs rather than a perfect circle. At ultraviolet and infrared wavelengths, however, its shape becomes clearer, revealing a zone where star formation is concentrated. The ring is not a narrow line, it is a broad region containing many clouds associations of young stars, glowing nebulae, and dark lanes of dust. Some parts are dense and active, while others are weaker or interrupted. The pattern is uneven because the material is not distributed smoothly. Gravity, rotation, earlier interactions, and local cloud motions all shape its structure. The ring, therefore, resembles a connected system of star-forming regions rather than one continuous wall of matter. Young stars make the ring especially visible in ultraviolet light. Massive blue stars emit strongly at short wavelengths, but they live for only a brief period compared with lower mass stars. Their presence shows that star formation has occurred recently in cosmic terms. Ultraviolet images reveal clusters and associations arranged along the ring, tracing places where cold gas has collapsed. These bright populations fade after several million years as the most massive stars exhaust their fuel. Infrared observations provide a different view. Dust grains absorb ultraviolet and visible light from young stars, warm slightly, and release energy at longer wavelengths. This makes dusty star-forming regions glow in the infrared even where visible light is partly blocked. The ring, therefore, appears bright in both ultraviolet and infrared images for different reasons. One wavelength traces the young stars directly, while the other traces the dust heated by their radiation. Star formation begins inside cold, dense clouds. Most hydrogen in ordinary interstellar space exists as separate atoms, but within the densest regions, atoms combine into molecules. These molecular clouds are cooler and more compact than the surrounding gas. Gravity can gather parts of a cloud until they collapse into smaller cores. As each core contracts, its center becomes hotter and denser, eventually forming a new star. Groups of stars often emerge from the same cloud over a limited period. Andromeda's star-forming ring contains neutral atomic hydrogen across a wide area, while molecular gas is more limited and concentrated. The galaxy forms stars at a slower overall rate than the Milky Way. Observations indicate that Andromeda contains less cold molecular material relative to its large stellar mass. The ring remains active, but its activity is modest compared with galaxies undergoing intense bursts of star formation. Its young stars appear in scattered complexes rather than across the whole disk. The ring's origin is not known with complete certainty. One possibility is that it develops from the internal movement of gas through Andromeda's disk. Spiral density patterns can compress material at preferred distances, helping gas accumulate into a ring. Another possibility connects the structure with gravitational disturbance from a companion galaxy. A passage through or near the disk can launch waves that move outward, gathering gas into a circular or nearly circular pattern. Some models associate the ring with an encounter involving Messier 32. In these models, the compact companion passes through Andromeda's disk and creates expanding density waves. The event can produce a large outer ring and a smaller inner feature. Other studies find that the observed structure may require a more complicated history or different orbital conditions. Observations support the importance of interaction, but they do not yet identify one exact sequence that explains every part of the ring. The ring is slightly displaced from the precise center of Andromeda. This offset may reflect past disturbance or an uneven distribution of gas. It may also arise partly from the viewing angle and from differences between the stellar and gaseous structures. Detailed maps show that the ring is not perfectly circular. Some sections curve into spiral-like segments, and some gaps may be caused by local conditions rather than a complete break in the underlying pattern. Gas inside the ring follows Andromeda's general rotation, but local motions complicate the flow. Clouds move relative to one another, expand after being heated, and are pushed by winds from young stars. Supernova explosions add further energy when massive stars end their lives. These events stir the surrounding material and create cavities, shells, and compressed edges. New stars may form along some compressed boundaries, while other regions lose the cold gas needed for further collapse. The life cycle of a star-forming complex is therefore temporary. A cloud gathers, cools, and fragments. Stars appear within its densest parts. Their radiation then heats nearby gas, while stellar winds push material outward. The most massive stars later explode and disperse additional matter. After several tens of millions of years, the original cloud may no longer exist as one coherent structure. The young stars remain and gradually spread along their orbits around Andromeda. Clusters in the ring range from loose associations to more compact groups. Many will not remain bound for long because their stars move apart after the surrounding gas is removed. Others may survive as open clusters for hundreds of millions of years. Their ages help astronomers reconstruct when different parts of the ring were active. A concentration of clusters with similar ages may record a wave of star formation moving through a region. Chemical enrichment also occurs within the ring. Massive stars create heavier elements in their interiors and release them through winds and explosions. This material mixes with the surrounding gas, although the mixing is not immediate or uniform. Later generations of stars may form from clouds containing a slightly greater abundance of these elements. Across long periods, repeated cycles of birth and death slowly change the chemical composition of the disk. Seen across Andromeda's full scale, the star-forming ring is a luminous band within a much larger and quieter galaxy. It concentrates much of the present creation of new stars into one broad orbital zone. Its ultraviolet light marks short-lived massive stars, while its infrared glow reveals warm dust and hidden clouds. The ring remains uneven, dynamic, and slowly changing, shaped by rotation, gravity, cloud collapse, stellar feedback, and the lasting effects of galactic interaction. Within Andromeda's star-forming regions, gas and dust gather into clouds shaping the texture of the disk. These clouds are part of the interstellar medium, the material occupying the space between stars. Most of their mass is gas, especially hydrogen and helium, while dust contributes a small fraction. Even so, dust has a strong effect on how the galaxy appears because it absorbs, scatters, and re-radiates starlight. The gas exists in several physical states. Some hydrogen is ionized, meaning its electrons have been removed by energetic radiation. Some remains neutral, with atoms moving through cooler regions of the disk. In the coldest and densest clouds, hydrogen atoms combine into molecules. Each state responds differently to heat pressure, gravity, and radiation. The boundaries between them are not always sharp, and one large cloud can contain several phases at once. Neutral atomic hydrogen spreads widely across Andromeda's disk. Radio telescopes detect it through a faint signal produced when the internal alignment of a hydrogen atom changes. This emission passes through dust and allows astronomers to map gas that visible light cannot reveal. The resulting maps show long structures, broken arcs, holes, and concentrations. These patterns trace the motion of the disk and the effects of stellar activity over large distances. Molecular hydrogen is harder to observe directly because cold molecules emit weakly under galactic conditions. Astronomers usually trace molecular clouds through carbon monoxide, which produces detectable radio emission. The amount of molecular hydrogen is then estimated from the carbon monoxide signal. This conversion is uncertain because temperature, density, radiation, and chemical composition affect the relationship. Even with these limits, observations show that molecular gas is concentrated in particular parts of Andromeda's disk. Dust is mixed through these gaseous regions. Individual grains are extremely small, comparable to smoke particles. They contain compounds rich in carbon, silicon, oxygen, iron, and other elements created by earlier generations of stars. Dust forms in the cool outer layers of aging stars in expanding stellar winds, and within material released by supernova explosions. Some grains are later destroyed by shocks or intense radiation, while others grow by collecting atoms inside dense clouds. When starlight passes through dust, shorter wavelengths are scattered and absorbed more strongly than longer wavelengths. This process makes distant stars appear dimmer and redder. In Andromeda, broad dust lanes cross the bright background of the stellar disk, especially on the side tilted nearer to Earth. Their dark appearance does not mean they contain empty space. They are dense foreground structures blocking part of the light from stars behind them. Absorbed energy remains, dust grains warm and emit radiation in the infrared. Some remain very cold and radiate at long wavelengths, while smaller grains can be heated briefly by single photons and release energy at shorter infrared wavelengths. Observations across several bands allow astronomers to estimate dust, temperature, and mass. These measurements reveal clouds hidden from visible light images and show how strongly nearby stars heat their surroundings. Gas clouds are not static objects with fixed edges. Their interiors contain turbulent motions across many scales. Portions of a cloud move together, collide, compress, and separate. Magnetic fields thread through the gas and can influence how material flows. External pressure from warmer surroundings adds further structure. A cloud may appear coherent in one observation, while higher resolution reveals smaller filaments, knots, shells, and cavities. Gravity becomes important, where cold material gathers into a limited region. If internal pressure and turbulent motion can no longer support the cloud, part of it begins to collapse. The collapse is rarely uniform. Dense filaments divide into smaller cores, and each core may form one star or a compact group. Most of the original cloud does not become stellar material. Radiation, winds, and later explosions disperse much of the gas before it can collapse. The chemistry inside dense clouds differs from that of exposed gas. Dust shields the interior from ultraviolet radiation, allowing molecules to survive. Atoms and molecules collide with grain surfaces where some combine into new substances. Ice can form around cold grains containing water, carbon monoxide, methane, ammonia, and other simple compounds. These materials remain microscopic, but they influence cooling and provide ingredients that may later become part of planetary systems. Andromeda's dust content is not distributed evenly. The inner disk contains prominent lanes, while other regions have less obscuring material. Metallicity affects how much dust can form because grains require elements heavier than helium. Gas that has experienced more generations of stellar enrichment usually supports more dust. The relationship is not exact, since destruction, growth, and transport also matter. Local conditions therefore create variations from cloud to cloud. Clouds move with the general rotation of the disk across broad regions, but they also respond to spiral structure and local gravitational forces. As gas enters a denser region, it can slow and compress. Collisions between clouds may increase pressure, although such collisions do not automatically trigger star formation. Some encounters simply disrupt the clouds or stir their interiors. Whether collapse follows depends on temperature density, magnetic support, and the strength of the disturbance. Massive young stars rapidly alter the clouds that create them. Their ultraviolet radiation ionizes nearby hydrogen, forming glowing regions of plasma. Stellar winds carve bubbles into the surrounding gas. When massive stars explode, shock waves expand through the cloud and can destroy dust, heat gas, or compress distant material. These effects are called stellar feedback because newly formed stars change the conditions for later star formation. Feedback can both suppress and encourage collapse. close to a powerful star gas may be heated and scattered, ending local star formation. Along the edge of an expanding bubble, material can accumulate into a dense shell. Parts of that shell may later collapse if they become sufficiently massive and cool. The result is an uneven sequence in which one generation of stars clears some regions while compressing others. Across Andromeda's disk, gas and dust record this cycle of gathering, cooling, collapse, heating and dispersal. Their dark lanes reveal where visible light is blocked, while their radio and infrared emission exposes the material itself. They provide the raw substance for new stars and carry elements returned by older ones. Though thin when averaged across the galaxy, they form dense local clouds that govern the changing appearance and continuing evolution of the stellar disk. Across Andromeda's inner disk, stars of many ages and compositions occupy the same rotating system. Some have formed recently from cold gas, while others have traveled around the galaxy for billions of years. Their light slowly blends into the broad glow seen from Earth, but careful observations separate this mixture into distinct populations. Each population preserves information about when it formed, what material was available, and how the disk has changed through time. The youngest stars are hot, bright and blue. They form in groups within dense clouds because massive stars live for only a short time. Their presence identifies regions of recent star formation. They emit strongly in ultraviolet light. Their numbers are limited compared with older stars, yet their brightness makes them prominent in images of active parts of the disk. Less massive young stars shine more faintly and survive much longer. Many remain hidden within clusters or associations where they form together. As these groups age, their members drift apart under the influence of internal motion and Andromeda's gravity. Some clusters dissolve within a few 100 million years, while others remain bound for longer. Their gradual dispersal spreads young stars through the disk and makes their common origin harder to recognize. Intermediate age stars occupy a broader range of environments. These stars have survived long enough to complete many orbits around Andromeda. Their birth clouds have disappeared and their original clusters may no longer exist. They include stars similar in mass to the Sun. Their colors and brightness help astronomers estimate the history of star formation across the disk over several billion years. The oldest disk stars are often cooler, fainter, and more widely distributed. Many formed when Andromeda contained less material enriched by previous stellar generations. Their orbits tend to be less confined to the narrow gas layer. Repeated gravitational disturbances slowly increase the range of their motions, producing a thicker distribution above and below the plane. This gradual heating of stellar orbits does not raise temperature in the ordinary sense. It increases the variety of stellar speeds and directions. Astronomers describe stellar populations partly through metallicity, the abundance of elements heavier than helium. A star's composition reflects the gas from which it forms. Early generations contain fewer heavy elements because fewer stars have yet produced and released them. Later generations can form from gas enriched by stellar winds and explosions. In Andromeda's inner disk, many stars contain more heavy elements than populations in the distant halo, though the distribution remains broad. Metallicity is measured from patterns in starlight. Different elements absorb specific wavelengths, leaving narrow features in a spectrum. The strength of these features depends on composition, temperature, and gravity at the star's surface. By comparing observations with models, astronomers estimate the abundance of iron and other elements. Large surveys then reveal chemical trends across the disk. These measurements show that Andromeda contains overlapping groups rather than one uniform stellar population. A general chemical gradient extends from the inner disk towards the outer regions. Stars and gas nearer the center often show greater enrichment because star formation has occurred there over many cycles. The trend is not perfectly smooth. Stars can migrate from one orbit to another without being strongly heated. This movement mixes stars born at different distances and weakens the original chemical pattern. Mergers add further complexity. A smaller galaxy entering Andromeda can deposit stars with distinct ages, motions, and chemical signatures. Some become part of the halo, while others settle into or pass through the disk. Gravitational disturbance can also move existing disk stars into new orbits. The inner disk therefore contains stars formed locally alongside stars influenced by external events. Their present location may differ greatly from their place of birth. The motions of stars provide another way to separate populations. Young stars and cold gas generally follow nearly circular paths close to the disk plane. Older stars show a wider spread of speeds and more vertical motion. Some rotate slightly more slowly on average because their elongated orbits carry them inward and outward across the galaxy. Spectroscopic observations measure motion along the line of sight, while models reconstruct the broader pattern from many stars. Andromeda's steep inclination makes this work difficult. Multiple layers of the disk overlap from Earth's viewpoint and dust blocks some regions more strongly than others. A telescope may collect light from stars at several distances within the galaxy along one sight line. Astronomers use color brightness, velocity, and chemical composition to separate these components. Infrared observations help by passing through dust more easily than visible light, revealing stars hidden in obscured regions. Variable stars add precise information. Some stars change brightness in regular ways, connected to their true luminosity. Cepheid variables are young massive stars whose pulsation periods reveal their intrinsic brightness. RR Lyrae stars are older and less luminous, tracing ancient populations. Comparing their true and apparent brightness helps measure distance, while their distribution reveals where populations of different ages are concentrated across Andromeda. Red giant stars provide a broad map of older populations. They are luminous enough to be detected individually across much of the galaxy. Their colors respond to both age and chemical composition, so interpretation requires care. Groups of red giants can reveal regions with different histories, especially when combined with spectral measurements. Their numbers show that Andromeda's disk contains an immense foundation of evolved stars beneath the brighter pattern created by young populations. Stellar remnants also belong to this population. White dwarfs remain after stars similar to the Sun lose their outer layers. Neutron stars and black holes form from more massive stars, though most are difficult to detect unless they interact with companions or surrounding material. These remnants contribute little visible light, yet they preserve the endpoints of earlier generations. Their presence is inferred from stellar evolution, explosive events, and compact binary systems. Across the inner disk, the mixture of stars forms a layered record of Andromeda's development. Young stars identify recent cloud collapse. Intermediate-age stars trace long periods of steady formation. Ancient stars preserve conditions from earlier stages, while chemical differences record repeated enrichment and mixing. Their orbits show the effects of rotation, migration, and disturbance. Together, these populations reveal the disk not as one generation of stars, but as a vast overlapping history, carried through moving points of light. At the center of Andromeda's disk, the central bulge rises as a dense concentration of stars. It appears bright because countless stars occupy a compact volume. From Earth, the bulge dominates the visible glow of the galaxy, especially through small telescopes, while the fainter disk extends far beyond it. This region is not separate from Andromeda. It is a major component formed through star formation, orbital change, and gravitational interaction. The bulge differs from the disk in both shape and motion. Disk stars generally follow paths close to a common plane and rotate in the same broad direction. Bulge stars occupy a thicker, more three-dimensional region. Their orbits are tilted, elongated, and varied. Many pass above and below the disk plane while circling the center. Together, these paths create a swelling of light extending beyond the thin disk. Most stars in the bulge are old. Their colors tend toward yellow and red because cool, evolved stars contribute much of the visible light. Bright red giants are especially prominent. Many have exhausted hydrogen in their cores and expanded into later stages of evolution. The bulge also contains many faint, low-mass stars that remain on the long, stable period of hydrogen burning. Their individual light is weak, yet their great numbers add to the dense background glow. The age distribution is uneven. Observations indicate that much of the bulge formed early, but smaller populations may have developed later or entered through mergers. Separating them is difficult because stars overlap along every line of sight. Dust blocks some regions and the steep viewing angle compresses a deep three-dimensional structure into a narrow image. Infrared observations help by passing through dust more effectively and by emphasizing the cooler stars that dominate the bulge. Chemical composition also records the bulge's history. Many of its stars contain substantial amounts of elements heavier than helium. This enrichment shows that earlier generations have processed their birth gas. Supernova explosions and stellar winds release newly created elements into surrounding space, allowing later stars to form from richer material. Some stars remain metal-poor, showing formation across several stages and gas histories. The distribution of metallicity changes across the bulge. Some regions contain a greater fraction of enriched stars, while others include more ancient, metal-poor populations. These differences may reflect separate episodes of star formation, mixing, or the addition of stars from disrupted systems. Astronomers compare spectra from thousands of stars to map these patterns. Their results show that the bulge is not chemically simple, even though its combined light appears smooth from a distance. Andromeda's bulge is unusually large and luminous compared with the bulges of many spiral galaxies. Its key prominence suggests a history that includes strong internal evolution and repeated gravitational encounters. A major merger can drive stars into varied orbits and build a rounded central component. Smaller mergers can also add mass gradually. Internal changes within the disk may move stars inward, especially if an elongated bar transfers angular momentum. The relative importance of these processes remains under study. The shape of the bulge may not be perfectly spherical. Observations suggest that it has an elongated or box-like structure when viewed in 3 dimensions. Such shapes can arise from a bar seen at an angle. A bar is a broad concentration of stars following elongated orbits through the inner galaxy. Over time, part of a bar can thicken vertically, creating a form that resembles a box or peanut when viewed from the side. Andromeda's inclination makes this structure difficult to observe directly, but models reproduce several features of its inner light. Stars in the bulge move rapidly because the gravitational field is strong. Their speeds vary widely in direction, producing what astronomers call velocity dispersion. This term describes the spread of stellar velocities around an average value. A high dispersion indicates that stars do not share only one orderly circular motion. Measurements of this spread help estimate the mass contained within the bulge and reveal how its stars are supported against gravitational collapse. Rotation also contributes to the bulge's motion. The region is not entirely random. Many stars retain a shared sense of movement inherited from the disk or from earlier structures. The balance between rotation and varied orbital motion helps determine the bulge's shape. A system supported mainly by rotation tends to appear flatter, while one supported mainly by velocity dispersion appears rounder. Andromeda's bulge contains elements of both behaviors, producing a thick, luminous form with complex internal movement. Stellar density rises steadily toward the inner part of the bulge. The average separation between stars decreases, although direct collisions remain rare because stars are extremely small compared with the spaces between them. Gravitational encounters still influence their paths over long periods. Binary systems, compact remnants, and dense star clusters exist within the crowded environment. Their interactions can produce variable stars, bright X-ray sources, and occasional explosive events, though most stars continue their evolution without close contact. Dust lanes cross portions of the bulge and alter its apparent brightness. Some dust belongs to the inner disk, lying in front of the central light, while other material may occupy the bulge itself. The dust creates patches and asymmetries in visible images. Infrared maps reveal a smoother distribution beneath this obscuration. Correcting for dust is essential when astronomers estimate the bulge's true luminosity, stellar mass, and three-dimensional shape. The central bulge contains far less cold gas than the star-forming ring. Most of its visible mass is locked in older stars. Star formation continues at only a limited level because dense cold molecular clouds are scarce. The region, therefore, shines mainly through populations created long ago rather than through abundant new stellar birth. Its light is steady on human time scales built from countless aging stars moving through a deep gravitational field. Its light, therefore, combines ancient formation with later structural and chemical change. Within Andromeda's structure, the bulge forms a dense transition between the rotating disk and the most compact central region. It gathers ancient stars into a thick, luminous volume, preserves chemical evidence of early enrichment, and records the effects of mergers and internal orbital change. Its rounded glow is the brightest part of Andromeda seen from Earth, yet even this concentrated light arises from a system of many populations, each following its own path through the crowded center. At the deepest visible part of Andromeda, the light of the central bulge narrows into a compact and unusual nucleus. Early observations show that this nucleus does not appear as one simple point. Instead, it contains two main concentrations of starlight, separated by only a few light years. From Earth, these features lie so close together that only high-resolution instruments can distinguish them. Their arrangement gives Andromeda what is commonly called a double nucleus, although the structure is not two independent galactic centers. The brighter concentration is often called P1, while the fainter concentration near the true dynamical center is called P2. These names describe observed peaks in brightness rather than separate objects with equal status. P1 contains many stars gathered near one side of the nucleus. P2 lies closer to the point around which the innermost stars move. The difference between brightness and gravitational center is the key to understanding why the nucleus appears divided. The most widely accepted explanation describes the double nucleus as an eccentric stellar disk. Eccentric means that the stellar orbits are elongated rather than circular. Many stars travel around the same central mass on aligned elliptical paths. They move more slowly near the far ends of their orbits and spend more time there. This crowding creates the brighter peak, called P1. Near the opposite side, the stars move faster as they pass closer to the central mass, so the light is less concentrated. The orbits remain organized because the stars share a similar orientation. If their elongated paths pointed in random directions, the nucleus would appear smoother. Instead, the aligned disk produces an uneven distribution of light. Gravity from the central mass dominates the motion, while the self-gravity of the stellar disk may help maintain the common pattern. Computer models show that such an arrangement can remain stable for a long period under suitable conditions, though its exact origin is still uncertain. At the center of P2 lies an even smaller concentration of hot blue stars, sometimes called P3. These stars occupy a region only a fraction of a light year across. Their blue color indicates relatively high surface temperatures. They are younger than most stars in the surrounding bulge, or they may include evolved stars whose light resembles that of a younger population. Observations favor a compact disk of relatively young stars, but the details of their formation remain difficult to explain. The true center contains a supermassive black hole. Its mass is estimated at roughly 100 million times the mass of the Sun, with measurements varying according to the model and data used. This black hole is far more massive than the one at the center of the Milky Way. Its gravity controls the motions of stars within the innermost region and provides the central focus of the eccentric disk. The black hole itself emits no light, but the paths of nearby stars reveal its presence. A black hole is a region where gravity becomes so strong that matter and light cannot escape once they cross the event horizon. The event horizon is the boundary beyond which return is impossible. For Andromeda's central black hole, this boundary is tiny compared with the stellar nucleus surrounding it. The observed peaks of light extend across light years, while the event horizon spans a far smaller distance. Telescopes therefore detect the effects of the black hole rather than a direct image of its edge. The stellar speeds near the center rise sharply as distance decreases. Spectra reveal how quickly stars move toward or away from Earth. By mapping these velocities across the nucleus, astronomers estimate the amount of mass required to hold the stars in orbit. The concentration of mass is too great and too compact to consist only of ordinary stars or dark stellar remnants. A supermassive black hole provides the explanation consistent with the observed motion. Despite its great mass, the black hole is quiet. Andromeda does not contain a bright active galactic nucleus powered by large amounts of infalling gas. Only a small quantity of material reaches the region where it can heat strongly and radiate before crossing the event horizon. The resulting emission is weak compared with active galaxies. This low activity may reflect the limited supply of cold gas in the central bulge and the difficulty of removing enough angular momentum for matter to fall inward. Hot gas still surrounds the black hole and some material may move toward it. Magnetic fields, turbulence, and collisions can heat this gas to very high temperatures. A portion may be expelled before reaching the event horizon. The faint radiation varies, showing that the central environment is not completely still. Even so, the total energy output remains modest for a black hole of such mass. The blue stars of P3 orbit within this quiet environment. Their presence creates a puzzle, because strong tidal forces near a supermassive black hole can disrupt ordinary star-forming clouds. Dense gas may still collapse under special conditions, or the stars may have formed farther away and moved inward. Another possibility is that interactions among older stars create objects that appear younger. Observations support the existence of the compact blue population, while its exact history remains uncertain. The double nucleus also changes slowly through gravitational motion. The eccentric stellar disk may precess, meaning that the direction of its elongated orbits rotates around the center over time. The rate depends on the black hole, the mass of the disk, and the surrounding bulge. Small disturbances can alter the alignment, yet the observed pattern shows that the structure remains coherent at present. Its persistence places limits on models of how the nucleus forms and evolves. At this innermost scale, Andromeda's vast dimensions narrow into a region governed by one compact mass. The galaxy's outer companions, halo, disk, and bulge, all belong to the same gravitational system, but the central few light years follow the black hole most directly. Stars crowd along aligned elliptical orbits, producing two peaks of light around one true center. Within them, a small blue cluster circles close to darkness. The structure is not a pair of galactic hearts, but a single nucleus whose uneven starlight reveals the precise geometry of motion around a supermassive black hole. Its center remains quiet. Andromeda now rests in silence across the northern sky, its faint light carrying the memory of millions of years. The galaxy remains immense, yet its scale becomes calm when considered layer by layer. The distant companions continue along slow paths. The dark matter halo holds its unseen shape. Ancient stars drift through the outer regions, while streams of debris preserve the outlines of vanished galaxies. Thin gas surrounds the system, moving gradually between the galaxy and the wider local group. Closer to the disk, stars follow broad rotations through warped planes and spiral patterns. Dust clouds gather cool and divide. Young stars appear inside dense regions, while older stars continue around the center through long and steady orbits. The bright bulge rises from the disk as a deep concentration of ancient light. At the center, the double nucleus remains bound around one supermassive black hole, where motion becomes faster and distances become small. Across every region, Andromeda is not a fixed picture. It is a changing system held together by gravity. Stars form and fade, gas moves inward and outward, satellite galaxies lose material, stellar streams widen and blend into the halo. These processes unfold so slowly that the galaxy appears still, yet its stillness contains continuous motion. The light reaching Earth shows Andromeda as it was long ago. Its present state remains hidden behind the time required for light to cross the space between galaxies. The view is therefore both real and delayed, a quiet record carried through darkness. Andromeda remains a neighbouring galaxy vast beyond ordinary measure, yet ordered by the same physical laws that shape every star-cloud orbit and grain of dust within it.